Now we're going to look at a few approximate Riemann solvers, and there's a wide range of approaches that are used for defining approximate Riemann solvers for different problems. I won't try to cover everything in this lecture, but just give you an overview in particular of a couple different methods, the HLL method and the row solvers. There are some Jupyter notebooks that illustrate this in our book on Riemann problems and Jupyter solutions. In fact, a whole section of that book is about approximate solvers, so there's, I think, 5 different notebooks. In particular, a lot of what I'll talk about today is in this shallow water approximate notebook listed at the bottom here, but there's also one on Euler equations, for example, and comparison of different approximate Riemann solvers. And again, there's various different ways that Riemann solvers can be approximated. So if you're using a flux differencing method where the solution is simply written, or the method is written in conservation form as a flux difference, then one way you might think about using an approximate Riemann solver is to somehow define the flux at the boundary as an approximation to the correct flux of Godunov's method that would come from looking at the exact solution along the ray x over t equals 0, and instead look at some approximate solution. What value does that have along that ray, and use that as your approximate Riemann solver for, say, a first-order Godunov method, and then perhaps generalize that to higher order by looking at a higher order time stepping or some other extension of the flux differencing method to higher order accuracy. But what I'll focus on is, again, the wave propagation approach, where we look at solving the Riemann problem at each of the cell interfaces, and then using the waves that come out of those Riemann problems, not only to define the first order Godunov update, but also to apply high resolution correction terms to get something more like second order accuracy, with the addition of limiters as discussed in the last lecture in order to avoid oscillations. So what we want to look at now is how can we get approximate waves that we can use in this wave propagation algorithm without solving the full Riemann problem. Also, we're going to be approximating all of the waves in the Riemann solution by simply discontinuities propagating at constant speed. So we aren't going to be modeling rarefaction waves in their entirety. And as we've seen for the scalar problem, you can often get away with that as long as your rarefaction wave is always going entirely in one direction or the other. But in the transonic case, where the rarefaction wave is sort of spanning the cell interface, then these sort of approximate Riemann solvers may give methods that converge to an entropy violating solution, and so we need to incorporate also an entropy fix in order to get the right solution. And I'll look very briefly at one approach to doing that at the end of this lecture. So again, the wave propagation methods, we think of solving the Riemann problem by splitting up the jump between two cells as a sum of a set of waves with some speeds associated with them. And then we use these waves to update the neighboring cell averages depending on the sign of each speed. It either updates the cell to the left or the right, and we've written that sort of in terms of fluctuations. But we can also look at these waves as giving a characteristic decomposition of the slope, qi minus 1 over delta x, and so we can add them in as second order correction terms with some limiters applied in order to avoid oscillations. So the idea of an approximate Riemann solver is we want to approximate our Riemann solution by some set of jump discontinuities that we can use in that wave propagation algorithm. And there are various approaches to do this. So one possibility is just ignore the fact that there might be rarefaction waves and the integral curves in phase space, and instead look only at the Hugonio loci and find Riemann solutions that consist of a set of discontinuities propagating at speeds that satisfy the Rankine-Hugonio jump conditions, which in some cases may be physical shock waves, and in other cases might be non-physical entropy violating shock waves. But that would give you one way of defining an approximate Riemann solver, and we did that for the scalar case, for example, and we saw that that works just fine as long as you're not in the transonic rarefaction case. But if we look at doing this for a system, even if we ignore the rarefaction waves, we still have to find the intersections of these shock Hugonio loci, and that can be expensive. So in this lecture, we'll look at a couple of other approaches. One is originally due to Harten-Hyman Lear, the HLL approach, in which regardless of how many equations there are in your system and how many waves there are in the true solution, we use a simple approximation where there's only two waves at some specified speeds, and there's a single intermediate state that's then uniquely defined by conservation. And then the second approach that we'll look at a little later is the local linearization, where we replace the nonlinear problem by a linear system, but we define a different matrix A hat at each cell interface based on the values to the left and the right. And A hat should be some approximation to the Jacobian matrix, but there are certain conditions it has to satisfy in order for this to work well. So we'll look at that later. But let's start with this HLL approach. So the main idea here is regardless of how many equations we have, we specify some values S1 and S2 that are supposed to approximate the minimum and maximum characteristic speeds around this Riemann problem in some sense. We'll talk about how to do that in a moment. But once we've defined S1 and S2, then we look for some state Q star so that we can simply define our waves as W1 and W2 moving at those speeds. And then we want it to be conservative. So in general, when we have this wave propagation form, and we've written the jumping Q as a linear combination of waves, then when we look at the conservation law, what we find is that the sum of S times W has to be equal to the flux difference between the left and right state. As long as that's true, then you can use these two waves in the wave propagation form, and you'll get a conservative method. You can rewrite it in conservation form if you want. And once you impose that, then that gives a unique solution for what Q star is, provided S1 and S2 are different, then and the denominator is non-zero, there's a unique value Q star that gives us conservation. And that's all there is to it really for the HLL solver, except that you have to think about how do we define S1 and S2. So we might have some sort of upper and lower bounds of the expected speeds and eigenvalues over the entire problem, or we might do it more locally. Typically, we do something where the S1 and S2 are chosen separately for each Riemann problem depending on the states QL and QR. So for example, we might, if we have expressions for the eigenvalues of the Jacobian matrix, we might look at the minimum and maximum values that the derivative f prime of Q can take at the left state and the right state. So we can just calculate those values. So for the shallow water equations, for example, the eigenvalues are U minus square root of GH and U plus square root of GH. And so we might take, for example, S1 to be the lambda 1 eigenvalue in the left state, and S2 to be the lambda 2 eigenvalue in the right state. And assuming that S1 is less than S2 here, that can be a reasonable choice. Turns out for some choices of Q left and Q right, you might not have that ordering. And so you might want to take S1 to be the smaller of UL minus the square root of GL, GHL, and UR minus the square root of GHR, for example, and use the maximum of the characteristic values in the right state as your S2 value. But for the examples I'll show, we can just use these two choices. Well, if you use those, then the formula for Q star from the previous slide just becomes this, and I just wrote it out in detail down at the bottom here just to show you that it's a relatively simple expression for the shallow water equations. There's no need to solve a nonlinear equation to look for this intermediate state. It's just a simple combination of the left and right state. So here's an example. If we use, for example, the shock speeds, well, here I've kind of cheated. I've used as S1 and S2 the shock speeds that come from the exact two-shock solution. So I've taken the state QL and QR, and I solved the exact Riemann problem to figure out where the intermediate state is that can be connected to a one-shock to QL and by a two-shock to QR. So that's sort of the all-shock Riemann solution. And if I calculate those shock speeds and then use those as S1 and S2, then for this system of only two equations, if I use the exact shock speeds in this formula, then it turns out that the HLL solver actually reproduces exactly the right intermediate state. So in this case, the Q star that comes out is exactly the right location. But to do that, I had to choose S1 and S2 to be very particular values that were actually the correct speeds coming out of the Rankine-Hugoniot condition. And as I said, that's kind of cheating because if we're trying to do an approximate Riemann solver, we don't want to have to solve the exact Riemann problem in order to get those values. So more realistically, we might choose S1 to be the characteristic u minus the square root of gh at the left state, and S2 to be u plus the square root of gh at the right state, because those are things we can evaluate from the initial data without knowing the solution. And if you do that and plug it into this HLL formula, you get a Q star that's not the exact solution of the two-shock Riemann problem, but it's not too far off. And how far off it is will depend very much on how far apart these states QL and QR lie. Here's just one more example where I've chosen a QL that has positive velocity, a QR has negative velocity, but they have similar sort of depths. And in this case, the exact solution would be here. The exact intermediate state would be here. In this case, we have positive velocity in the left state, negative velocity in the right state with similar jumps. So we actually have two shock waves in this case, and the exact intermediate state would be here. But the Q star that comes out of the HLL solver, if we use, again, evaluating the eigenvalues at the left and right state to give an approximation to S1 and S2, our Q star ends up over here, for example. But it depends very much on what I used. If I make a different choice of S1 and S2, it will lie someplace else. So we might say, instead of evaluating those characteristic values or eigenvalues right at these two states, suppose we just have some upper and lower bounds on S1 and S2 over the entire, or over some portion of the phase plane. Maybe, for example, we assume that S1 lambda 1 is always greater than or equal to minus 2.5, and S2 is less than or equal to plus 2.5. So those are the values I've used here. And with the same QL and QR as before, we now get a Q star state that lies a little to the left of the correct point rather than being off to the right of the correct point. And if you made this sort of range of estimates larger and larger, if I made S1 very negative and S2 very positive, then the Q star would tend to lie more and more at just sort of an average value somewhere in between QL and QR. You show when the limit is as S1 and S2 go off to plus and minus infinity, that we are just sort of averaging QL and QR for our intermediate state. So the closer you can do to approximating the correct shock speeds, the better it's going to look. Also, if you were looking at just a very small jump in Q, so if the delta Q between the left and right state is very small, so here I've zoomed in on a smaller portion of the phase space, so I've got a state Q left and Q right that are actually quite close together in phase space, so that the integral curves or shock Hugoniot look roughly linear over this space, and the eigenvectors are roughly constant over this space. Then if we use the eigenvalue at the left and right state, the eigenvalues are also roughly constant over this region, and we'll end up with a Q star that's actually very close to the correct solution. And this is important because if we're looking at a realistic problem where we have maybe some regions of smooth flow separated by a few shock waves, then where things are smooth, as delta x goes to 0 as we refine the grid, we expect the jump in Q, delta Q, between two adjacent cells to also be going to 0. It should be order delta x. So over most of the region of space where the solution is smooth, we really expect to be solving Riemann problems like this, where Q left and Q right are very close to each other. And so any Riemann solver that can do a good job of approximating this case should work well on smooth flows. But then if there's some strong shock waves separating portions of smooth flow, then you also have to worry about doing well on those shock waves too. Also, this is for a system of two equations, the shallow water equations, so an HLL solver, which is only using two waves, is adequate and can really approximate well the full solution in this situation. But if we go to something like the Euler equations with three equations and we use an HLL solver that only has two waves, then no matter how close the states are to each other, we're not going to be capturing the full structure, including the contact discontinuity. There's actually an extension of HLL called HLLC, which I won't talk about in detail, but the C stands for contact, and it's a sort of a version of HLL that adds a third wave to represent a contact discontinuity in the very important special case of gas dynamics. And because gas dynamics has this linearly degenerate contact discontinuity wave, it's relatively easy to figure out how would you add a third wave and still make the solver very efficient to implement. But rather than pursuing that, let's look at this other approach to approximate Riemann solvers, which is based on local linearization. And again, replacing the nonlinear problem by a linear system where the A hat matrix is chosen locally at each Riemann problem to be an approximation to the Jacobian. So as the left and right states approach some common value, whatever formula we use for A hat should approach just the F prime at that common value. And so then the idea is if we can define a matrix A hat that has that property and that is also has real eigenvalues and linearly independent eigenvectors, so that the linear problem we've defined here is hyperbolic. And if we can easily compute the eigenvalues and eigenvectors of that matrix, then we can solve the Riemann problem approximately by simply taking our jump-in Q and splitting it up as a linear combination of the eigenvectors of the matrix A hat. And define the waves then as those scaled eigenvectors. And for the speed, we'll use the corresponding eigenvalue of A hat. So that depends on being able to define some sort of reasonable average Jacobian. There's lots of ways to do that. You could just take the average of F prime at Q left and Q right, or you could take F prime at the average state. But you'd also like that to have eigenvalues and eigenvectors that are easy to compute. Well, since we know the eigenvalues and eigenvectors of F prime, say for shallow water equations in general, then either of the two averaging methods I just mentioned could be used to calculate the eigenvalues and eigenvectors of F prime. So we could take, for example, A hat equals F prime evaluated at 1/2 QL plus QR. And we know formulas for the eigenvalues and eigenvectors of that Jacobian matrix at that state for shallow water equations, say. But it turns out there's another condition that we would really like to have satisfied on this A hat, which won't be satisfied by what I just wrote down there. But before going into that, I did want to mention that there's a couple of different ways you might use this Riemann solution if you've defined it this way. So one way you could use it is to, once we have this approximate Riemann solution, that gives us for any left and right state, that gives us a set of waves that are propagating at some speeds. And we could look now along this ray x over t equals 0 and just see what is the value along that ray. And the value along that ray would be the value in the left state plus the sum over all the left-going waves of the wave strength. Or you could also start with qi and subtract off all the waves that are right-going. But either way, you get some value for q star along the interface here. And then just evaluate the flux function, the true flux function at that value q star, and that would give you an fi minus 1/2 that you could use directly in flux differencing. Or if you wanted to rewrite it in fluctuation form, you could define the fluctuation, left-going fluctuation, to be the difference between that interface flux and f in the cell on the left. and the right-going fluctuation to be the difference between F in the cell on the right and the interface flux. Same way we did when we looked at Gottnoff's method for a scalar problem, for example. So that's one way to use it, but another way to use it that's a little more convenient in the way propagation form is to define the fluctuations to be simply the sum of the speed times the wave summed over all left-going waves for the left-going fluctuation A minus, and similarly for A plus dq, sum up S times W over all the right-going waves. And if we looked at the, say, an exact Riemann solution that consisted only of shock waves, then this formulation would be identical to this other formulation. But more generally, if we define the waves and speeds to be eigenvalues and eigenvectors of some other approximate Jacobian matrix, then we haven't really done a flux vector splitting. And so in general, this would not be conservative if we use this formulation down below. The only way it can be conservative is if the sum of the left-going and right-going fluctuations actually add up to the flux difference between the two cells. That's certainly true for this formulation up here. If you just add the two together, the interface flux drops out and you get exactly that condition satisfied. But that won't be true in general if you define the S's and W's as eigenvalues and eigenvectors of some other matrix that's just defined as some kind of average without thinking carefully about how to impose this condition. So this, what we call the row solver, is a particular choice of this linearization that does satisfy this condition. So it turns out that in order for this condition to be satisfied, what we need to check is that our matrix A hat satisfies A hat times the jump in Q is equal to the jump in F. So again, A hat depends on Q left and Q right. So we have some formula for A hat as a function of Q left and Q right. But it should have the property that the jump in Q, for the particular jump that defined this matrix A hat, should satisfy A hat times the jump in Q is equal to the jump in F. And that won't be true in general if you just define A hat to be the average of the Jacobian on the left or the right, or if you evaluate the Jacobian at the average state. Neither one of those will exactly satisfy this condition. But if you do satisfy this condition, then you have various nice properties. You do, it is a good approximation of the Jacobian matrix. You can think of this as being sort of an approximation to the A hat being the derivative F prime of Q, at least in a particular direction. And more generally, we also want A hat to approach F prime as Q right and Q left approach each other. So for weak waves, smooth flow, as we saw for the HLL case, we'll get good approximations in that case. And not just for systems with two equations, but even for larger systems, because now our A hat matrix is the same size as the Jacobian and has the same number of waves as the true Riemann solution. But it also has some other nice properties. In addition to working well for smooth flow, it turns out that it can capture a single shock wave exactly. So what do I mean by that? Suppose that Q left and Q right are two states that actually satisfy the Rankine-Hugoniot condition. So the jump in F is actually some scalar multiple of the jump in Q. Well, if that's true, then we also know that the jump in F is A hat times the jump in Q. So that means that A hat times the jump in Q is equal to S times the jump in Q, and therefore the jump in Q must be an eigenvector of A hat, and S must be the corresponding eigenvalue. And so when we solve the linear problem with this same data, QL and QR, the solution of the linear problem, Riemann problem, will consist of just a single wave, because the jump in Q is an eigenvector of that matrix, and it will be moving at the correct speed. So the row solver has the nice property that not only does it approximate smooth flow well, but also it can approximate a single isolated shock quite well. And again, most realistic problems, you have maybe smooth flow separated by shock waves that are moving through the smooth flow, but often the shock waves are sort of moving through smoothly varying flow, and so most Riemann problems, you either have small jumps or else you have a jump that corresponds to a large shock wave in one family and small jumps in the other families that correspond to whatever smooth flow is going through the shock wave. Only rarely do you actually have two shock waves colliding with each other and producing two strong shock waves coming out of it. So the row solver might not work quite as well in that case, but for almost all of the Riemann problems you encounter in solving a problem over time on some grid, usually it's either smooth flow or it's one strong shock and smooth flow in the other families, and the row solver handles both of those quite well. Moreover, it turns out to be conservative. Of course, for a single shock, if it's going to capture it exactly, it's being conservative there. But more generally, the way that we define the fluctuations in general to be the sum of the negative part of the speed times the wave, or the positive part of the speed times the wave, if we add those two together, then that adding up the negative part of SP to the positive part of SP just gives us the total SP. So we end up with just the total of SP times W. But since these W's were eigenvectors of the matrix A hat, SP times A times W is simply A times W. And then we can pull the A hat out of the sum. And then the sum of the W's is exactly the jump in Q. So the sum of the fluctuations is simply A hat times the jump in Q. But then this condition up here says that that's equal to the jump in F. And remember, this is exactly the condition we need for the algorithm, the wave propagation algorithm, to be conservative, that the sum of our fluctuations that we add into the cell on the left and what we add into the cell on the right should add up to the flux difference. So let's look again at the shallow water equations. And for the shallow water equations, how would we define such a thing? Well, it turns out, again, you have to take a very special sort of approximation. The right approximation to take here is to define an average depth. That's simply the arithmetic average of HL and HR, but define an average velocity that's not at all intuitive. It's sort of the average of UL and UR, but weighted by the square root of the depth on either side. So that's a weighted average of U left and U right. And then to define A hat based on these two states, we simply evaluate the Jacobian matrix at this H hat or H bar and U hat values. So it's the true Jacobian evaluated at a particular average state, but it's a very special sort of average. And in the book, I go through why this particular averaging works for the shallow water equations, and there's something very similar for the Euler equations. Instead of weighting U by the square root of H, you rate U by the square root of the density rho in that case. So it turns out if you define your average in this way, then this rho condition is satisfied, that the A hat times the jump in Q equals the jump in F. And so we have these nice properties. An isolated shock is modeled well, the wave propagation algorithm is conservative, and we can use these waves and speeds to also define higher order correction terms and apply limiters. And again, the eigenvalues and eigenvectors, we have analytic expressions in general for any Q hat. And so here I've defined Q hat based on these H bar and U hat, and those are the eigenvalues and eigenvectors. And if we look at the same examples we looked at a moment ago for HLL, then this intermediate state Q star lies very close to the true solution of the Riemann problem in this first case we looked at. And also in the second case we looked at, it's quite a bit closer to the correct solution than the HLL approximation, for example. Oh, in the Jupyter notebooks, there are other examples, and there's also widgets that you can play around with or just change things and re-execute the code in order to move around the left and right state and get an idea for how these approximate Riemann solvers work more generally. Also, some of the plots produced there are like the one here, where in addition to the phase plane on the top, we also show the solution in the xt plane, and then show what h and hu look like as functions of x at particular times. And again, they're self-similar, so as time varies, those waves simply move out. So what we see in this particular Riemann problem is that the middle state is close to the true solution, and that shows up in these plots as h in this intermediate state is close to the correct value, and also hu is close to the correct value. And then we also see that in the Riemann, or in the approximate Riemann solution, we've approximated things with two waves that come out of this linear system, and so we have two jump discontinuities, whereas the true Riemann solution had a rarefaction wave. So over here in the xt plane, we see the blue lines are the rarefaction wave. The green ray is simply the propagation of the discontinuity. And in these pictures, we see again, there's a discontinuity instead of a rarefaction wave in the left-going wave in each case. There's also an example shown in the notebook and discussed a little bit in the finite volume book about the fact that the row solver can be inaccurate, and in fact can sort of be disastrously inaccurate in some cases. In particular, it can sometimes give you an intermediate state that's not at all physical. So here we look at a problem where the velocity initially, it's this example where the depth HL and HR are initially equal, but the velocities are outgoing on both sides. And if you have just a small enough velocity jump relative to your jump in h, then what you get is two rarefaction waves that move out with some lower depth in between. But if you put a large enough velocity there, then the state in between is quite small. So what we see up here is the black curve here is the true solution, and the zero line is here, and the true depth in the middle is very close to zero. And in the phase plane, that middle state lies here, and this is plotted now in the phase plane where we have h on one axis and u on the other side, rather than hu. And the true solution consists of two rarefaction waves with this middle state. But when you apply the row solver to this particular case, you end up with an intermediate state in your row solver that's over here with negative value of h, which is completely non-physical. So mathematically, that's a perfectly fine solution. You can work out where that intersection is, but you find a depth of minus 0.5 here, which just doesn't make physical sense. And the reason is that these integral curves in the HU plane are varying rapidly enough near the h equals 0 axis that the row solver for these states is simply not capturing that well enough. And you can sort of see what the problem is here, that the wave speeds that have been chosen by the row solver are too small. And so when we computed this row solution, it has to be conservative, so it has to have the same total mass as the true solution, the black curve. But because these waves are moving much too slowly here, in order to get the right integral, it had to have a much lower value here than what the true solution has. So this is a case where actually the HLL solver would do a much better job, because if we looked at the HLL solver and we used as our two speeds the limiting or the characteristic speed lambda 1 in the left state and lambda 2 in the right state, then those are the speeds at which the edge of the rarefaction wave are moving. And so if we put our discontinuities out here rather than at the locations given by the eigenvalues of the row matrix, then to conserve mass, we would have ended up with a solution that looks more like that perhaps. And it still wouldn't be a great approximation to the true rarefaction waves, but at least the depth would stay positive in between. So it turns out you can kind of combine the best of both worlds for some systems, at least. to do a modification of the HLL method that also uses some information from this row solver. And that's what's done in what's called the HLLE method. This is just actually the same figure I drew a moment ago, slightly different scale here, but these are the two waves that come out if we take the speed to be the lambda1 of q left and lambda2 of q right and plug that into the HLL solver. And now the HLL intermediate state lies in the region where the depth is clearly positive. So the HLLE method in general the E is for Einfeld. This was an extension of the HLL solver proposed by Einfeld because he had been running into similar problems in gas dynamics where you can, with the row solver, compute intermediate states that have negative density in that case, but the same idea works for shallow water. And this is again a two-wave solver like HLL, but it chooses the characters, or it chooses the speeds S1 and S2 by looking at both the characteristic speeds and also the eigenvalues of the row matrix that we were just looking at. I just noticed a typo on the slide that I just fixed. This should be lambda sub I minus 1p used in defining S1 and lambda sub IP used in defining S2. But the idea is that we look at, over all of the characteristic families, we look at the smallest value between the eigenvalues of the true Jacobian in the state to the left and the row eigenvalues, and use that for S1, and for S2 we maximize over all families and the true eigenvalue in the right state or the row eigenvalue. And so if we do this, then it turns out you can show that for gas dynamics and also for the shallow water equations, you get a solver that is guaranteed to remain positive and never has a negative density in gas dynamics or a negative depth in shallow water equations. Also, you can show that if you use this choice in the HLE approach, then if the Riemann solution consists of a single shock, then in that case, you're using this row speed and the exact solution is obtained from the HLL solver the same way it is from the row solver. So it inherits that nice property from the row method. And also, no entropy fix is needed if you do it this way. Turns out by sort of forcing the wave speeds to be large enough, you put in enough numerical diffusion that you don't need to worry about adding an entropy fix, at least for these particular examples. Whereas with a row solver, a transonic rarefaction wave can easily be approximated by a discontinuity that's moving at speed close to zero and does not spread things out nearly enough. So let me just finally briefly mention how one approach to an entropy fix works if you're using, say, the full row solver. But this could be applied really to any method that splits up the jump in Q into some set of waves propagating with some speeds, lambda p hat. And the idea is that for each of the families, or for at least the families that we think might have a transonic rarefaction wave, depending on the data, and for something like gas dynamics, we know the two wave is always a contact discontinuity, so we don't have to worry about that one. But for the one wave and the three wave, we might do something similar. Once you've defined your waves, your splitting of the jump of Q into waves based on your approximate Riemann solver, whatever that is, in the Kth family, we can define the state between Qi plus all of the waves with index less than K, and the state to the right of that jump, which is that same state plus the jump across wave K. So picture is we have a bunch of waves, and if we're looking at one particular family, then we looked at the left state and the right state corresponding to this wave, which is propagating at speed lambda k hat. this case k would be 3, I guess, for the system of 4 equations, and we were looking at the jump across the 3 wave. And then the case where we have to worry about a transonic rarefaction is if we evaluate the eigenvalue lambda k in the state that's just to the left of that wave, and we evaluate it just to the right of that wave, and if they have this property that to the left it's less than 0 and to the right it's greater than 0, then that suggests that this wave in the k family should really be a rarefaction wave, and not just any rarefaction wave, but one that's transonic, that's spreading across the 0 line. And so that's the case where we want to replace our jump discontinuity with some smoother rarefaction wave, ideally. But again, we're looking at approximate Riemann solvers, so we don't want to compute the exact rarefaction wave solution. So the idea is that instead we'll think about splitting this one wave. So we should have sort of a rarefaction wave, say, in this one particular family, and instead we have just a single wave moving at one speed, but we're going to split it up into 2 waves that are going at one going at a negative speed and one going at a positive speed, so that we can spread the effect of this wave between the cells to the left and the right of this interface in a better way that hopefully respects the entropy condition. So the idea is that we'll split this one wave into a left part and a right part that have speeds that are negative and positive, and the speeds are simply the exact eigenvalue evaluated at sort of these approximate states, QKL and QKR, to the left and right of this one wave. And this value beta here, so we're going to kind of split it up into some fraction beta of the wave, and then the remaining part, 1 minus beta times the wave. And the way we'll choose beta is to require conservation. So in the wave propagation form, we're usually adding in lambda k hat times wk as a contribution to one of the fluctuations. To make sure the fluctuations still add up to the flux difference, we have to make sure that now that we've split things into 2 waves, that we have the sum of lambda times w for those 2 waves equal to what it was originally. And if you just plug these 2 formulas into this relationship, then you come up with this value of beta. And in terms of implementing this in the wave propagation form, we do something similar to what we do for the entropy fixed for scalar problems. We leave this wave wk alone in terms of computing the high resolution correction terms and the limiters and all of that. And all that we do is modify the fluctuations that are used in the Godunov update in a way that we spread things more properly between the left and right cell in this case. And so the usual wave propagation form, again, we define the left-going fluctuation by taking the negative part of each eigenvalue times the wave and summing over all the waves. So that's just adding up the contributions from the left-going waves, and a plus delta Q similarly adds up only the contributions from the right-going waves, lambda times W for the ones for which lambda is positive. And normally we define the negative and positive part of lambda to be just the usual thing. But in order to extend this to this entropy fix, we can simply use these same formulas here, but redefine what we mean by lambda k minus and lambda k plus to be, instead of the negative or positive parts, which would always mean one of them is non-zero and the other is 0, instead we'll make them both non-zero. One of them is beta times lambda lk, which is negative, and the other is 1 minus beta times lambda kr, which is positive. So we split up this one wave into one bit that's left going, one bit that's right going. So one of them will come into a minus delta Q and the other one will come into a plus delta Q. And so information is spread to both neighboring cells. And notice that when we plug these into this expression, for example, lambda k minus times wk, now with this beta in here, we can write that as lambda kl times beta wk, and beta wk is sort of the wave strength of this modified wave from the previous slide that we want to view as the left-going wave. Similarly, on the right-going side, 1 minus beta wk is the right-going fraction of that wave that gets multiplied by lambda kr. But we can sort of group the beta and 1 minus beta with the lambdas in order to make this implementation a little nicer. So that was kind of a quick overview of a couple of different approaches to approximate Riemann solvers and how you might do an entropy fix. There's, as I said, many different methods that have been developed over the years for approximate Riemann solvers and extending these sorts of ideas to much more complicated systems of equations that come up in other applications. And there are some more references in the book. And again, I encourage you to look at the Jupyter notebooks and play around with those a bit to get a better feeling for what's going on with these methods.